Hypothesis tests population for variance and standard deviation. You have to remember that the variance is the standard deviation squared. Sometimes they give you the standard deviation, and if you need the variance, you just square it. Sometimes they give you the variance. If you need the standard deviation, you would take the square root of it. So those two things work together. The variance is the standard deviation squared. It says the human resource department of a major corporation announced that the number of people interviewed by the corporation in 1 month has a mean of 104 and a variance, the standard deviation squared, of 233. The management of the corporation suspects that the variance exceeds 233. A random sample of 18 months yielded a mean of 99 interviews with a variance of 441. If we assume that the number of people interviewed by the corporation in 1 month follows an approximately normal distribution, is there enough evidence to conclude at a 0.1 level of significance that the management's claim is correct? What was their claim? Their claim was that the variance exceeds 233. The variance is the standard deviation squared. If I exceed something, I'm going to be, what math symbol? Greater than 233. Okay? So, that doesn't have the equal. We know that's our alternative hypothesis. The standard deviation squared, or the variance, is greater than 233.
Are we on homework 17?
Yes, we are. Number 7, day 17, way up there at the top. It says that.
I don't have that one.
It should be with your 16 that we did last time. So maybe you pulled it out of your notes. 16 and 17 were together, but we only did one homework page because we did our assessment. So we did 16, but we didn't get 17 done.
This one, right?
There's 16. Oh, maybe did I have to print that for you? Yeah, I'll probably have to print this one for you too, because then you must have been missing both of them, I'm going to guess. Let me print that quick here. All right.
Thank you.
Yep. Now we'll see if it wants to write exceeds greater than 233. That should kick out here in a minute. It's got to warm up probably. So if we know the alternative hypothesis is that our variance is greater than 233, that means the null hypothesis would be the variance is less than or equal to 233. The null always has the equal and would be the opposite of whatever that one is. So it just depends on our statement. We are doing a one-tailed test. Our one-tailed test is checking, are we greater, because we always compare it to this, to the 233. So my alternative hypothesis would be in that section. My null hypothesis would be in that section that I'm trying to test. Again, we are going to do, if we're doing standard deviation, the chi-squared test. The chi-squared test, I can't remember if it had the word or if it had the symbol, is the one that looks like x squared, but it's really read chi-squared. So I can't remember, but for some reason I wrote the degree of freedom down there. So it might have chi-squared and then you might have to put the degree of freedom. I can't remember for sure which way you have to do that. We'll figure out what the degree of freedom is in a minute. So when we are doing our test statistic to find chi-squared, we are going to do the standard deviation squared, which is actually your variance, times n minus 1 over the population standard deviation squared. So you have your sample standard deviation squared, or your variance of your sample, and sample variance, and then you have the population variance. So, in there, it tells me my sample variance. I have a random sample of 18 months, yielded a mean of 99 with a variance of 441. That's the sample, right? So my sample variance, my S squared, is at 441. The population variance is going to be the one that they gave you.
Wait, is
That
that,
we're
is that,
Oh, I said 441 and I wrote 444, didn't I? That won't work very well. Let's fix that. Thank you. 441. So my population variance, that other weird symbol, is going to be the one that you have in your problem. Just like on the regular mean. So it's going to be the 233. What else do we need here? We need N. N is 99, right? There are 99 interviews, right? N. Wait a minute. Never mind. If I read the question right. In a random sample of 18 months, we had a mean of 99. My sample was 18 months. There's my N. N is going to be 18. So I mentioned earlier when you do chi-squared, just like when you do the t-test, you have to do the degree of freedom. Whenever you do the degree of freedom, it's always N minus 1. So my degree of freedom is going to be 18 minus 1, which is 17. I think they have it where you have to pick out the symbol chi-squared, which looks like x squared, and then you put the degree of freedom of 17. Otherwise, I don't know why I would have written that down. In my formula, then, for my test value, my sample variance was 441. I'm going to take that times the n minus 1, which is 17, and I'm going to divide that by the given variance that I'm comparing it to, which is the 233. So at least that one's easier to type into your calculator. What did you get when you put that in there?
I don't know if this is right.
It's a little bit off because you put 223 on the bottom and we were supposed to have 233 on the bottom.
Oh, I bet.
Try it again with the 233 down there. But it is kind of a big number.
Is it 32?
Yep.
176?
Yep. 32.176 is our test statistic. So, we are going to do a p-value test. So that means on the Alex calculator you're using the p is greater than, right? The p is greater than, and we're doing chi-squared. Now again, because we are doing a greater than here, we don't have to do the 1 minus. If it was a less than, we'd do the 1 minus. So we're going to just use p of chi-squared is greater than, or 32.176 with a degree of freedom of 17, right? And that's going to give our percentage we're going to compare it to. What do we get when we calculate that? So keep in mind, if it's a greater than, we just use the p of whatever. If it's a less than, 1 minus p of whatever, just like on our other tests.
.014.
0.014, yep. That's what we should be getting. We are going to compare that to the level of significance, right? Whenever we do the p-value test, we're comparing our percentages. Our percent that we came up with was 0.014. We're testing it against 0.1. Is that less than or greater than? It's less than. So if that's a less than, what do? We reject the null, exactly. Reject the null. That means the null is not true, and the alternative is the true statement. The true statement is that my variance is greater than 233. Now we got our weird question. Can we support the claim that the variance of the number of people interviewed by the corporation in 1 month exceeds 233? At least it says the not reject thing. I don't hate it when it says that. So, can we say that the variance is greater than 233? Yes, we can. That was our true statement. Our true statement says our variance is greater than 233. So, yes, we can support that claim. All right. Number 8, IQ scores. IQ scores among the general population have a mean of 100 and a standard deviation of 14. A researcher claims that the standard deviation of IQ scores for males is less than 14. A random sample of 19 IQ scores for males had a mean of 102 and a standard deviation of 9. Assuming that the IQ scores for males are approximately normally distributed, is there significant evidence at the 0.05 level of significance to conclude the researcher's claim is correct? What in the heck was their claim? The researcher claims that the standard deviation is less than 14, right? See that sentence there? So this one we're doing standard deviation, not variance. And so my standard deviation symbol is that crazy one that looks like that. And the claim is it less than 14, right? That's what it says. Is it less? Which means on our one-tailed test, we're testing to the left. Again, this does not have the equal in it, so that's my alternative hypothesis. Is it less than 14, which means it goes in there. That means my null hypothesis is my standard deviation greater than or equal to that 14, right? My null hypothesis, that'd be in that section over here then. So, on our formula says we're taking s squared times n minus 1 over the standard deviation squared. Notice we just have the standard deviation. So we're actually going to do the squaring as opposed to when they give me the variance, I just use the number that's there. So that's why they did them both kind of together. So in this case, S, my sample standard deviation is 9. So that means in my formula I'm going to do 9 squared. I'll jump to the n. My n. How many people did I have in my sample?
102.
No. A random sample of how many? 19, right? It says we did a random sample of 19 scores. The n is 19. Gives us the mean. We don't even need the mean in this problem. It gives us the mean, but we don't need it. So we're going to do 19 minus 1. In other words, 18 there. Over, and then our standard deviation, the one from the problem, is 14, right? And so on the bottom, we're going to do 14 squared. if you want to make it easier to type in, you could just do the 19 minus 1 in your head. Oh, I forgot to pick out my test statistic. My test statistic is the chi-squared. The degree of freedom is my n minus 1. So my degree of freedom is going to be my 18, right? Probably should put that in there. So my degrees of freedom, n minus 1, 18. So we're going to do 9 squared times 18 divided by 14 squared to find the value of our test statistic.
No.
7.439. Okay. 7.439. I wrote 2 different things there. Now I'm trying to figure out which one was the one I wanted. I think it's the bottom one. So, we are doing a left-tailed test, but we're doing this critical value. On the critical value, because this is over in this section, the 95 or the what percent are we looking at? 5% would be this section, and we want this section. When we do the critical value for this one, we are going to do the chi-squared, and we're going to do 1 minus that critical value. Instead of just using the 0.05 like we normally get to do on the chi-squared, if we're going to the left, we're going to do 1 minus that with a degree of freedom, of course, of 18. So I think you can either type it in with the 1 minus, or you can just do the 1 minus in your head and just put in the 0.95, whichever way you want to put it in there. That's why I wrote 2 things, I think. So you're going to do, since I'm doing a critical value, the chi-squared sub. Oops, yours keeps going to sleep on us, huh? See the chi-squared sub on there? It's that one. Yep, that one right there. And you can either just put in the 0.95 or 1 minus 0.05. And my degree of freedom is 18. Yep. All right. So, we get 9.390. That means this value right here is 9.390. That's my critical value. So keep in mind when it does the critical value, if it's a left-tailed test, you got to subtract that. If it was a right-tailed test, then you could just use that number that was there. But left-tailed, you got to do 1 minus that. Kind of like the P thing. On this then, my test value is 7.439. Would my test value fall on the left side or on the right side of my critical value? On the left side, right? My test value, 7.439, falls in this section. So that means it falls in the section of our alternative hypothesis. So that's going to be my true statement. This is going to be my not true statement then. The true statement is that my standard deviation is less than 14. So, can we support the claim that the standard deviation for males is less than 14? Yes, that's my true statement, right? My true statement says yes, it is less than 14. I like it better when it says support and not reject. Support's easier to figure out. All right, one last one on this page. Number 9. A new sleeping pill is advertised to increase the daily sleeping times of insomniacs by an average of 2.9 hours with a variance of 0.35. The government group conducts an independent study on the new pill claiming that the actual variance of increase in sleeping time is different from the advertised variance. The government group tests 20 insomniacs chosen at random with the new pill. The insomniacs report a mean daily sleeping increase of 2.9 hours with a variance of 0.57. Is there enough evidence to conclude at the 0.05 level of significance that the government group is correct? Assume that the increase in the sleeping time provided by the new pill is normally distributed. Notice it says perform a two-tailed test. If it's a two-tailed test, it's not a greater than or a less than, it's a not equal to, right? Anytime it says it's a two-tailed test, I'm testing not equal to. So is my variance not equal to the 0.35, which is what their claim is? So again, when I pick out where does that go, the equal has to go with the null. So is my variance equal to 35% or is my variance not equal to 35%? And again, this is a two-tailed test, so I'm going to have my H1s on both ends and my HO, my null, in the middle. Since we're doing a variance, we're doing our chi-squared. We have to put our degree of freedom in there, but we haven't figured that out yet, but we can. The degree of freedom is n minus 1. N, how many people did we survey on this one? 20, and so n minus 1 would be 19 for our degree of freedom. Since n is 20, 20 minus 1 is going to be 19 for our degree of freedom. All right, our formula that we had, s squared times our n minus 1 over our variance squared. So our sample variance says we have what? What's the variance from the sample?
So,
0.57, exactly. 0.57. That's going to go in for our s squared. Again, it gave us the variance, so we don't square it when we do our formula. If they give you the standard deviation, then we have to square it. So we're just going to use that 0.0, or is it 0.57, if I write the right thing down. 0.57 times n minus 1 would be our 19, right? That was our degree of freedom, over the sample, or the population variance. The population variance is the one from the problem that we're trying to compare it to, which is our 35%, right? So we're just going to take 0.57 times 19 divided by 0.35. And again, it's kind of a big number, or bigger than what we have been used to getting anyway. Yep. 30.943. Okay, we are doing a p-value. Anytime it says p-value, we know we're doing the p of something on our computer, right? When we do p of our chi-squared, again, it's testing to the right. So we're going to find this number here, which will match with this number here. So on our LX calculator, we're doing p of chi-squared is greater than are 30.943 with a degree of freedom of 19. .041, yep. 0.041. So if this is 0.041, that also means this is 0.041. Which means our p-value, we have to add them together or multiply by 2, right? My percentage, if one side is 0.041 and the other side is 0.041, then it's going to be 0.082, right? We're looking at a percentage. Now we're comparing that percent to our critical value. So 0.082, how does that compare to the level of significance? 0.05. It's greater than. And if my p-value is greater than my level of significance, what do I do? We accept the null. Accept that the null is true. So that means this is my true statement, this is my not true statement. Or my false statement, I suppose. Can we support the claim that the variance of increase in sleeping time using the new pill is different from the one given, whatever that says down there, from the one advertised? Can we support that it's different? No, we can't, right? If it was different, this would be the true statement. We're saying it's the same, it's equal to that. So can we support that claim? No, we cannot. Can't support the claim. That's the toughest part, is this part down here. At least for me, that was the toughest part. Trying to figure out the true, not true, is it this answer or this answer, and how weird do they have that worded down there at the bottom. Alrighty. I am going to let you work until about 4 o'clock. We may or may not get through the next homework page, but I've rattled your brain enough for a little bit anyway.
Using this for me?
Oh, is that other one? I'm just canceling that because you just did the midterm and got that done. And you probably haven't done any work on your pie chart since then, I'm assuming.
So you just log out and then log back in?
Yeah, just give me a second here.